My name is Devin Foxhoven. I am the team lead of this project. Accompanying me are my Scrum Master, Anthony Smith, and our dedicated developers, Brandon Wetzel and Kenneth Lee. Now, for this project, we worked alongside the Naval Undersea Warfare Center Division Newport, our client being Derek Wong, and Professors Irene Belova and the teaching assistant, Nathan LeBlanc, were key in helping guide us along this project to get it to the successful state it is in now. So, question is, what is the project? So, our project came along with the initial issue of submarines are extremely tight, compact spaces. It's very difficult to get a large number of people into a single small area. So when you need to start training electrical and mechanical repairs on a submarine, having hands-on training becomes very difficult. You can only usually have maybe one instructor or 2 to 3 students at a time. So what's the possible solution? Well, what if we get rid of the physical environment altogether? So what we did is we went ahead and tried to create a virtual reality simulation of a submarine-specific room. We go a little bit later detail on what specific room we did and why we chose it. But for the development of this, we ended up using Blender to create all of the assets for the scene, and then using Unity 3D to compile all these assets together to create an actual scene where you can walk around and interact with the objects. So, before we actually go into most of the details, we want to go ahead and get the live demo early on so that you guys can actually see what we're going to be talking about later on. So, get the scene going. Yep. All right. Apologies, VR headsets are a little bit fickle to work with. All right. So, as you guys can see in the scene, we have multiple different objects within the environment. The user is going to be represented by a pair of hands that they can walk around and interact with the objects. Now, what we did is we went ahead through all the objects and made different types of drives for different types of interactions. We have linear drives that are used for, say, drawers and cabinets. The cabinet doors themselves, along with, say, the pantry doors, these use a thing called a circular drive that allows objects to rotate. Now, with this, the user can walk around, interact with the different objects. As you can see with the oven, there is a button on the right-hand side that when interacting with it will actually turn a light on inside the oven. Now, a lot of these smaller interactions are just kind of proof of concepts to display the idea that you can bind certain actions to certain movements within the system. So this can be later on used for, say, electrical or mechanical repairs. An incorrect repair will not elicit the response you want, but a correct repair will actually provide a visible feedback for the users. So, the live demo is a little bit short, but what we're going to do is we're going to actually go into a video demo showing the networking and the multiplayer. So in the scene, if you want to have instructors and students, you need to have multiple people within a scene. So, starting off, it's a little bit difficult to see, but in the top left-hand corner, there is the option for the user to either host or join a server. So when the user hosts the server, their IP address becomes essentially the anchor for it. In order to join it, you input a specific IP address, and this would be, I apologize. All right, there we are. So when the client puts in the IP address, they automatically connect to the scene in which the host has created. As you guys can see in the scene, there is a blue dot. This represents a headset within the environment of another user. The hands that you can see from both the client and the host can interact with the different objects as they go through the scene. All right, this is being very okay, so we're just going to let the video play through. One of the key difficulties with trying to connect into the host client server is, unfortunately, with the limited time we have, we couldn't work on any of the security. So we had to shut down the firewalls in order to be able to connect directly based on the system networks that the school currently offers. But with this, you can see that myself in the scene opened up the door, and Anthony, who is the client, can still go through and close the door easily. There's a bunch of different network environments that you guys can see as you walk through. Movement is a little bit disconnected. This is mostly because of the hardware we had and the confined spaces for recording. Recording this in our dorm rooms, we had about a half-a-foot radius in order to move. So this offered a little bit of constraints physically. But as you can see, some of the interactions we interacted with, specifically from my end, and then the same objects can then be immediately interacted with by the client. So there is no immediate trade-off between the host and the client. You're not delayed or forced to wait in order to interact. That little bit of fun out the way. Alright, so apologies for that. So what we're going to go into next is kind of the development order we want to do. So the very first thing we had to do in order to create any part of the scene was actually create the physical objects. Now, Blender was the key component in making this. This allowed us to create the textures, create the physical objects, and compile them together to actually give them to the Unity team. From there, the Unity team was able to start creating and assembling a scene for a user to physically go inside of. Now, using Steamvr, this allowed them to create interactions, such as the opening the cabinet doors, creating the buttons that will trigger lights, and so on and so forth. From there, we ended up using a component called Mirror. Mirror is what we use for the networking. This allows us to connect multiple clients to a host. Now, to go into a little bit more detail, we're going to actually go through the asset creation. So, for the asset creation, submarines being the confidential information that they have, we could not get specific details on, obviously, the model of the submarine. So for this, we had to figure out how we're going to create this. Well, specifically, we went into a room that was the least amount of confidentiality, the kitchen. So for this, we ended up using public live photos from different online sources to just start compiling a map. Now, this map is a very rough blueprint, but it pretty much gave us a one-to-one ratio of where objects inside the scene go, how large the scene is, and what things will actually need to be interactive for the user. Now, from here, we ended up just using Blender to initially create the primitives. From there, different cube cylinders, objects like those were really easy to just start manipulating lightly, joining them together, and then cutting out shapes inside them to actually create the final objects that we wanted. From there, we could start getting into the textures. Now, texturing being a long and complicated process, we actually used an open source site called Polygon Textures that gave us these really high quality textures. Specifically, we use these for the metals, while we ourselves created the glasses and the plastics. Now, some of the applications, as you can see, we have some high-res objects within Blender. Unfortunately, these did not translate one-to-one to Unity. While Unity and Blender have a huge amount of integration with one another, there's still some high difficulties when using imported stuff, say, as a Blender textures. So, unfortunately, this created a couple of conflicts with, say, importing a model that, while the normal kitchen sink, came in the size roughly of a Roman Coliseum. Asset creation done, I'm going to hand it over to Anthony, who's going to start talking about the virtual reality end of it.
Hello. To start with, the key components, we use Unity, an open source game engine that is free until you start selling for commercial use. Then we have Steamvr, built by the company Valve, also to run Steam. They give us a lot of VR tools and allow their project to become hardware agnostic. And then we have Mirror for networking. So to get started, we're going to go with how we create the scene by taking all our Blender models and constructing the scene with a visual map that we had created for reference. And then going from there, we use Unity API to create some functionality. A lot of this is collision management and also just getting some information from the Steamvr API. And then I want to show you what our scene looks like at one point. This is not what you just saw. This is kind of one of the best representations we got of the scene. This is with Unity's default render pipeline. The problem with this is that when we're using VR, we have two lenses in the headset, so we are doubling the rendering budget we need. So we're rendering on two different screens at once. So this was insanely performance taxing and made it very difficult to use in VR. We're kind of aiming for a minimum frame rate per second. It's 90 frames per second, and we would see as low as 50. So we moved on to URP, but before I talk about that, this happens with batching. Batching is Unity grouping up similar meshes into one batch and sending that to the GPU for a render call. And what I can show you is with the default render pipeline, over there on the bottom right, we had batch counts anywhere from 1,000 to 4,000 batches per frame, with triangle and vertice counts of our meshes being in the millions. This is why we had a FPS range of anywhere from 40, 50 to 100, which wasn't what we were looking for, and that changes every second. So we moved on to the universal render pipeline. This gave us a lot of rendering optimizations, but it did significantly reduce the visual quality of our scene. We got our batch counts down by about a factor of 10, anywhere from 40 to about 100 to 400, depending on the frame. Our vertice and triangle counts became static. We got down from about 10 million a frame to 3,500 and 10,000 per frame, and that did not change based off the position of the camera, because in Unity, when we are facing our viewport camera into the scene, we are going to render every mesh in front of us, even if they're obscured by other meshes. So if we're looking towards the end of the scene that we're in, we can expect the default render pipeline to not be rendering much, and we'd have a more stable frame rate. But if you're looking towards the other end of the scene, even if we can't see most of it, we're going to be taking that performance hit. With the universal render pipeline, we didn't have this issue, so we lost a lot of visual quality, but we got a lot of performance back, which was our primary focus with VR. And again, so this is what it looks like now, and if we go back, this is what it looked like before. So we didn't take a big hit from that, but it did increase usability and reduce motion sickness, which is very common in VR, especially with the different movement types. Just some frames. So now we're going to go into how we made it VR enabled, which is through Steamvr and its API. So its API allows us to make this application hardware agnostic, because this is mainly commercial grade hardware, mainly for video games. So we use two different hardware kits. We use the Valve Index, which are the same company who made Steamvr, and Facebook or Meta's Oculus Quest 2. And we didn't have to do any additional development tasks to get them to be functional, because we could just go into their API and set our events to that without actually programming specifically for each hardware. And then up here, when we are creating our activity, there's three main methods we're using. We're using their interaction drives. In this case, the three that we mainly prototyped was throwable, for, say, I want to throw this laser pointer. Very physics-based, I can just grab it with my controller and just fling it across the room. Linear drives that we sell for our drawers, those are also physics-enabled by default. And then our circular drive, which is the most common, which is how we get it, such as like cabinet interactions. A lot of what Steamvr does is intended to be expanded upon, which is why it's open source, because by default, the circular drive doesn't have momentum, and we weren't able to get that implemented in time. But the whole point of Steamvr is to rapidly develop VR applications and create additional functionality as needed, which is why I say the button, we used a linear mapping drive, where all we could do was, once we got to the final state of the linear drive, we could call an event that would turn on and off the light. And then we move on to Mirror for networking. Mirror is based off Unity's deprecated networking solution, UNet. It comes with some built-in components and security, additional security that they handle themselves. We chose it because it was very easy to get. It's free to use, open source with pretty decent documentation, and easy to set up. We did learn that it had some drawbacks with VR, mainly due to a lot of things we're trying with nested interactions, and I can go into that a little bit later. So making it multiplayer, we had two big things we needed to make multiplayer. We needed the VR rig to be multiplayer, and we needed the interactions to be multiplayer enabled. To do the VR rig, we used two major components from Mirror: network transforms and network identities. The network identity is how the server identifies the game objects, all the individual components that make up the scene, to the server. And then the network transform, using client authority, and by default, when we spawn in a player in the server or a user, they will have authority over their rig. So network transform can be used to sync the local transform values, so our position and rotation, over to the server. This approach doesn't really work with our interactables. They're considered to be network scene objects, and because of that, the host of the server, by default, has authority over them, which means only they could interact with them, and then they would be synced across the server. We tried to make a dynamic system where upon grabs from the Steamvr API, we would just dynamically give authority. this ran into many issues, so we developed a new system that didn't require authority, which was our interactable RPC controller. And this doesn't require a network transform. So what we do is we're just going to be tracking on each client the position and rotation of an interactable. And if we determine if these values have changed, we can send a remote procedure call from the server to every client updating these values. This doesn't require that client authority that we were getting issues with. And then because of this, what we're doing, since all this is VR and all this logic is founded on Steamvr's API, which is existing only on the client, we couldn't really move that to the server to control the interaction, so we just want to track what is happening in the scene rather than letting the server dictate the VR interactions. So yeah, we went into the rig. So again, we have mainly 3 transforms we're looking at. The camera, which is the head, and then our 2 hands are the main things we're looking at. So we're just going to be updating continuously to the server to sync those values across every client. And then again, with the interactables, we're using that script where we are just tracking within a margin that we are setting to see how much something is moving and sending an RPC call to the server to all the clients. And then if it is on the server, then we can just send that, otherwise it's a command on the server end. And then one reason why we had issues with mirror and networking with VR is most people making making multiplayer application in Unity aren't really doing it for VR. And one issue is most of their components can't be nested. So let's say we had a lot of our doors have door handles that we will want to operate, and that would be a circular drive on top of the door with a circular drive. And to update both of those interactions, we would need to nest multiplayer components on top of them. Mirror does not allow that. So currently in our build, we can only track one interaction at a time. So we can only, mainly what we're just tracking is the door itself, not even the handle. So that is one limitation of Mirror that we had to deal with. So going into the tools we used Blender for 3D modeling. We used Unity for our game engine. Steamvr was great for rapidly creating VR functionality and making it hardware agnostic. We used GitHub for source control, and everything's written in C#. This includes the Steamvr APIs for Unity specifically is written in C#. Unity's APIs are written in C#, and all of our own source has been in C#. For communication, we use Slack, then Slack and Zoom for client communication, Discord for team communication, and then text and email as well for client communication. For documentation, we use the Atlassian suite, particularly Jira, and then we use Google Docs for our own internal documentation creation and storage. And that's all. Any questions?
Great job, guys. Just had a quick question. Obviously, VR is very CPU and GPU intensive.
Yeah.
I was wondering if you had any insight into testing or any of like the minimum requirements to use the system.
I will say, so most development testing was done on my machine, which has a GTX 1070. So you might know that's a little bit dated, and it is primarily for, like, say, for high 1080p frame rates or 1440p frame rates in a traditional monitor, not double rendering. So again, we were having the issue where I was seeing as low as 50 frames per second. And then furthermore, not that it's very common for most computer systems, but SLI, so a dual GPU setup, does not work with that. So you do want to look into better graphics cards. I believe, like, I have my roommate with a 1080 Ti, he can definitely run things better. I know we are running this on a 3070 right now, but he does have driver issues, so we didn't see any great improvement in performance, but that's not really a great test. But yeah, primary development was a 1070, so it could be, performance improvements could be gained from better hardware.
I do also know that we had a laptop in which we were running a Oculus Quest 2 on, and we saw no real drop in performance running on that. I know the laptop was using specifically a 3060 specifically designed for a laptop. So even with just like a little bit stronger graphics card on a laptop, ran no issues, no performance problems, nothing like that.
Awesome. So you've tested on multiple different configurations.
Yeah, we've had about 3 specific workstations in which we've been consistently using.
Excellent. Thank you. Great
And
job.
with the new render pipeline being so optimized, we don't really see any depreciable performance drops depending on performance.
Any more questions?
So you mentioned some of the compatibility issues between the models you build in Blender and the rendering engine. I'm curious whether you knew this before implementation starts, and if so, have you considered other 3D model builders?
So unfortunately, we didn't really know too much about Blender. When we initially got this project, none of us had any experience working specifically in Blender. So with some of the implementation issues, we weren't too familiar with which ones would come up as we started working. But as development started going more online, and we started getting more familiar with the actual development in Blender and how to create proper like collision boxes around the objects inside of Unity, I'd say between different softwares, Blender is still probably one of the more preferred ones, but a close one would probably be 3ds Max. I know I've used that one many years ago for modeling, and it does have some advantages over Blender in terms of creating a more universal work environment. But in terms of translating straight to Blender, straight to Unity 3D, I'm not too sure how compatible it is from there. I've never tested it myself.
Great, thank you.
So I have a question with respect to multiplayer. Can you have avatars? In other words, can you actually see the other people?
So if we had the time, we could have.
Yes.
But currently we didn't have the time, so we were just rendering the VR hands and then just a placeholder to show where the headset was. I do know that there are multiplayer VR applications that do have that functionality, so maybe even I think in Unity, so that's definitely a possible feature.
Yeah, interestingly enough, because on a submarine, besides it being small, there's a lot of people on it.
Yeah.
In which case you have to work around.
Yeah.
So I also like the choice of the galley, which a lot of people don't realize on the sub, food is a problem. Cooking for a whole crew around the clock is a problem. And oh, by the way, managing the food and the freshness, because fresh food doesn't last that long, is also a big problem. So it's actually a very relevant area of the submarine that you've modeled.
Yeah, it was our client Derek Wong's idea to do the galley.
It's actually a pretty good one, so good job.
There's also the only real room inside the submarine which we could get enough images of to get a somewhat respectable representation 3D-wise. Obviously, most of the other rooms don't have any images of them to actually be able to recreate.
Thank you, Devin and team.